Good day. My name is Kyle N. Caslin. This report will cover everything associated with my study, statistical forecasting of earthquake occurrence with appropriate caveats. Let's get started. This report covers the design and functionality of the earthquake flooding data, dashboards, overview, and its key features. Statistical forecasting of earthquake occurrence in the Philippines. Overview. The Philippines, situated along the Pacific Ring of Fire, is highly prone to seismic activity. This project presents a real-time interactive dashboard focused on statistical forecasting and monitoring of earthquake occurrences across various regions of the country. The goal of this study is to help visualize historical earthquake patterns, monitor current seismic events, and provide statistical tools for forecasting potential future earthquake based on the trends. Throughout the use of descriptive analysis, time series, and probabilistic model, example Poisson process, renewal model, Bayesian models, which users can explore earthquake activity across space and time. These tools can assess disaster preparedness efforts, regional risk assessments, and educational outreach by transforming raw data into understandable visual insights. The dashboards integrates filtering, geographic visualizations, and automated statistical summaries to promote intuitive explorations of seismic patterns in Luzon, Visayas, Mindanao, or any particular specific part of the country under the Philippines subregions. Key features: interactive statistic map with regional data, magnitude and deep filtering, time series visualizations for forecasting trends, and dynamic statistic and hotspots detections. Whether you are a teacher, researcher, student, policymaker, or citizen, this platform empowers you with up-to-date seismic data and advanced visual forecasting technique. Let's get started. This report covers the design and functionality of Earthquake Flooding Data Dashboard, which visualizes average earthquake magnitude by locating or depending on the locations in the Philippines. The dashboards consist of two main sections: the Visualization tab, which is this one, and the Analysis tab, which is this one. The Visualizing tab, it allows users to interact with the data through other filters such as a date range, province, and area based on the selected filters of the system. So we have here the filters. Computes and displays the average earthquake magnitude per location using an animate area and line chart. As you can see here, this is the one. It's still loading the data. As you can see, if you're going to hover or like try to pinpoint them out, it will show locations and the magnitude. Then this right here is the areas, the magnitude here, locations. Then another one is the Analysis tab, which provides a brief explanation of the chart, and the x-axis represents various geographic locations, while y-axis displays the corresponding average earthquake magnitudes. So users also have a guide on how to use the filters effectively to extract relevant insights. The dashboard uses Altair for interaction plotting and features animated graphs to enhance readability and storytelling, a progressive bars and percentage indicator from users of animated status. So from these visualizations, user can identify locations with high average magnitudes, clusters of consistent seismic activity, clusters of unusual outliers worth further investigation. So this tool processes a CSV dataset containing earthquake records, which we gathered from the PIVOX data. So this dashboard is practical examples on how data science and interactivity can support disaster preparedness, urban planning, and seismic research. Now let's move on to earthquake mapping. So, mapping dashboard. This report presents the Philippines earthquake mapping dashboard, a powerful visualization tools that layers geographic and seismic data to reveal earthquake patterns across the country. So the dashboard integrates five key layers, which is the scatter. Let's try to have it. Okay, so this is the five key layers: scatter layer, the 3D bar or the 3D column layer, the heat map layer, the text layer or text labels, then the arc, which is sequential arc layer, which is time based. So seismic, the scatter plot layer, which is the location epicenter map. Each dot, as you can see here, let's try to, yeah, just like this one. Each dot marks an earthquake position by latitude and longitude. Colors represents magnitude, light blue for weak, dark red for strong, making it easy to spot um, clusters. So next one of its layers is the 3D bars, or you can say the 3D column layer, which represent the magnitude by height. Earthquakes are visualized as vertical bars where height is equivalent to the magnitude. This layer highlights the strength of tremors across regions at a glance. As you can see the lines here, and with that, no, you can see the magnitude, the depth from to, which is the next area. Then the next one is the heat map layer, which spots seismic hotspots. It is a thermal overlay that shows high activity zones in red and yellow, helping identify frequent seismic zones over time. The next one is the text labels, which unmap magnitude levels. As you can see, there are labels. If you go into hover, try to pinpoint that with your cursor, it will pop up those informations regarding the earthquake incidents within the area of your choice. So the next one is the arc layer, which is temporal earthquake paths. Now as you can see here, there's arc. This is the what we call the sequential arc layer. This dynamic layer draws arcs between sequential events in the same province, revealing the progressions of earthquake over time, like connecting the dots on a timeline. You can see here that from South Orban to Sitangkal, so that indicates sequential arc layer. Together, this layer allows users to analyze where or how strong and how frequent earthquake occurs that will support, disaster readiness and spatial analysis. Now let's move on to earthquake data frame. So this interactive lineup chart represents a maximum recorded earthquake, which is depends on your pick. Select locations you can see here. These are the few selected um, locations. And each line represents a different area. This, as you can see here, with those locations helping identify patterns and seismic intensity. So x-axis, let's locate its neighborhood further to the most active, then y-axis magnitude values, richer scale from 0 to 10. So lines and shading, each colored of the lines and each shaded area represented. So the have here you can see the blue one Calarea, the orange is City of Canlaon, the green is General Luna, and so on and so forth. So then we have the interactivity. You can hover for detailed magnitude and area info or click the legend toggle. So as you can see, you go into toggle, try to point it out. There are details, right? If you want to this city of Canlaon, then the magnitude, they have its details. And if you wanted to switch to bar chart, you can also do that. You see, that's it. These visualizations highlight which locations and areas have experienced the strongest earthquakes, no? And it will support the comparative risk analysis and allows users to explore regional seismic behavior effectively. Now we also have the summaries, now location-wise statistics. You can see here. Then the overall statistic, total events, 122, average magnitude of 2.42, then maximum magnitude is 5.80. Now the date range, also have the date range on the fig. That depends on the filter data that you try to input or you try to filter. Statistical forecasting of earthquake occurrence in the Philippines. Here, we'll show how statistical models and interactive dashboards can help us better understand seismic risk, not to predict earthquakes totally, but to prepare more effectively. So as you can see, this is the features that it has. Map animations and full summary, earthquake data summary, total earthquakes, and then the sidebars here is the filter. You can select the years, then the provinces. So these total earthquakes are the combined numbers of earthquakes from the selected provinces, Calayan, Surigao, and Cotabato. Then the total date range, which is the selected years being pick of the filter that I choose. Then most active province from this three is Surigao. Then this is the average magnitude. This study uses statistical model to interpret seismic data from PVOX and convert it into useful visual and analytical insights. From daily and hourly trends to regional distributions, we use Poisson processes, exponential distributions, and Gutenberg-Richter law to build a comprehensive view of seismic activity. I'm going to show you later on what are those things that I use, kinds of models. So these models are applied and displayed through an interactive Python-based dashboard that allows user to explore earthquake pattern by year, hour, province, and magnitude. Is part of the chart and methods that can show hourly heat map. This figure shows earthquake frequency by the hour of the day, and the objective that it fills is that it will help model temporal distribution using Poisson and exponential processes, and also suggest time-based patterns for early warning or resource deployment. Most earthquakes happens between 3 p.m. and 9 p.m. That is based on the data that's been filtered, knowing that this allows agency to align monitoring system during these high risk. Then let's try to check another model. This is also part of the model of our system. Time interval distributions, which is time statistics. It will showcase or calculate how often earthquake happens after another, and most quakes happen just hours apart. So you can see they have average time between median, longest quiet period, then shortest quiet period. This supports the observations that earthquakes aren't random, but they often come in bursts. Now this is the time between earthquake distributions. The orange one is the actual time between, then the blue line is the exponential feet. Now it will showcase the days between earthquakes and also the probability density. Next one is the average monthly earthquake frequency. So you can see it has a peak data in November and also in August. This is based in the filter data that I picked recently, which is the three provinces and the specific year. Now this is the Gutenberg-Richter law. It also compare poison prediction earthquake counts to actual daily data and also have a probability of large earthquake. As you can see here, this is the Gutenberg-Richter distribution. The leg log 10 and then the magnitude. The observed is the orange dots and then the blue line is the fit, which is probability of 0.55 magnitude. Then the probability of large earthquake with this data in the Richter law is 5. Probability of magnitude 5.0 is 0.66%, but expected of magnitude 5 earthquakes per year is 12.29 based on the filtered data in the specific selections of province or area. Then this is the peak month analysis. You can see the highest activity that is in December and the average is 3,741 quakes with this data that is also based on the filtered scenario that I choose recently. Last one is the probability calculator. So you can see it will showcase now the number of earthquakes to calculate probability, then it will calculate. Probability of exactly 3 earthquakes in one day is 1.32%. Then probability of at least 3 earthquakes in one day is 99.46%, which is quite high. So that is all about with my studies.